just want to welcome everybody here today. My name is Gordon Hall. I'm the director of the Ethics Center here at UNC Charlotte, and I'm very pleased to welcome everyone here to our second talk in our series which is called Biased AI, which looks at different ways that AI's technologies do or don't function fairly in various social contexts. Before introducing our speaker, I want to do a little bit of advertising and promotional work. First, the next speaker in this series will be Alex Hanna of Google, talking on November 30th. It's called Algorithmic Unfairness, Infrastructure, and Genealogies of Data. I would show you the flyer for that, but we haven't made it yet. But Alex will be in this space on November 30th. Also, the center is running a second series this year. The first speaker for that will be on November 9th. I'm just going to pop up the flyer. The series is on African researchers' access to global research funding. And the first speaker, hopefully y'all can see that, Rafila Masekela, will be talking about global health. Is there a way to right the wrongs? And I am really excited to bring her to you from South Africa. Okay, so today's talk, Serena Wang is a PhD student at the University of California at Berkeley, who's doing some exciting work on educational technologies. And rather than misdescribe that work, I'm just going to turn the podium over to her to introduce it. So, Serena.
Hi, thank you, Gordon. I'm Serena, and yes, from UC Berkeley. And my work generally is in trying to ensure positive long-term impacts of machine learning in social good settings and also just in broader settings. And I do that through looking closely at algorithmic practices and also just developing algorithms in machine learning in general. Yeah, so today I'm going to be talking about our work in the education sphere, doing a sort of deep dive into some of the promises and pitfalls of machine learning for education. And before I dive strictly into education, I'm first going to talk a bit about machine learning for social good in general. So recently there's been this sort of burgeoning research agenda on machine learning for social good, where machine learning has been applied to a variety of applications from education or healthcare to environmental protection and the social sector and more. And there's been a lot of excitement and a lot of ways in which machine learning has maybe been helpful in these areas, but also ways in which it maybe hasn't necessarily delivered exactly what was expected or what was hoped for. And there's two prevailing challenges as we're still thinking about applying machine learning in these social good type areas and beyond. And the first is that, well, since these approaches are still fairly new and fairly recent, that empirical evidence on the long-term effectiveness of these different kinds of applications of machine learning for social good still remains sparse, given the recentness of these approaches. And the second prevailing challenge here, which I'm going to dive more into in this talk, is that there's limited inquiry into what social good actually really entails in these specific contexts often, and whether and how the machine learning efforts are really contributing to the relevant social goals. So throughout this talk, I will be diving into education as a specific case study of how we can study the second point in a deeper way. But throughout this talk, I would encourage you to keep in the back of your mind the ways in which these findings can generalize to other settings where machine learning is also applied. So why did we choose education specifically? Well, first, education is clearly, as people in education, we agree that it's a very important area. And also it's an area that has received a lot of attention from the machine learning community over the past, say, decade or so, where machine learning techniques are now prevalent in the education sphere, not just in massive open online courses, but also in higher education and K-12. And some examples are, well, people use, or machine learning is being used to predict student dropout risk. So in massive open online courses like edX and Coursera, machine learning is used to sort of predict a student's likelihood to drop out of a given course, or like to finish a course, to identify whether they need to like do some early intervention to keep the student like on track in these online courses. But this student dropout risk prediction is also used in K-12 and higher education as part of a system, like an early warning systems setup, where the idea is that they want to, if a student is maybe not on track for success, they want to identify that earlier rather than later. Another example is machine learning gets used for like automated grading and automated essay scoring. And this might happen in standardized testing, or on maybe on things like the GRE, or various other like K-12 types of standardized tests. And a related task is predicting test question difficulty, which may be used in the process of like developing standardized tests. And sort of related to that is this popular idea of like intelligent tutoring systems, where these are automated systems that are used by students to like work on specific types of skills, like maybe algebra, or things like it's like an automated tutoring system for certain tasks. And this would involve like getting some, maybe somewhere behind the scenes, they have some knowledge base from which they're gathering like data from teachers and whatnot, and then they translate that over to a student in an automated interface. The idea being that maybe you can like save time for teachers. Machine learning is also getting used in admissions, and we'll get into some example, like an example of that later, which you may be familiar with. But yeah, and then finally, in another higher education setting is machine learning gets used in chatbots for advising. These days, more and more of these are getting deployed, possibly maybe more now with the pandemic and move of a lot of things into more online interfaces. So machine learning is in a lot of places within education, and it's definitely kind of, there's even like still more settings that definitely have, like, this is definitely not an exhaustive list, but it is a list of examples of things which we've studied in our in this study. So machine learning has been used to like varying degrees of success in all of these different ways, and sometimes to sort of catastrophic failure. And one example of this recently is the grade algorithm for admissions at UT Austin. So a couple years ago, UT Austin started using this, the computer science department at UT Austin started using an algorithm for their graduate admissions to evaluate and rate the incoming applications. So the inputs to this were things like the GPA, student GPA, GRE scores, letters of recommendation, and personal statements, and other things around like the transcript. And the target was past admissions decisions. So they trained a machine learning model using these inputs to predict the probability that a student would have been admitted based on past decisions. And the usage of this model is that if grade predicts low enough, then maybe the rest of the admissions officers don't need to see it, or they say, okay, at this lower threshold, then the application may just be rejected without further review. I mean, there's some cases where I think the officers still could come in and review it if they chose to, but it was essentially used as this kind of like filtering type of cutoff. So this was used for a little bit, I think for like maybe a year or so. I don't know exactly how long, but last year it was pulled, and there was some like controversy surrounding it. And so UT Austin actually released this tweet saying, after the system was pulled, they released this tweet saying they're aware of the potential to encode bias into machine learning systems like grade, which is why they've now phased out the reliance on grade, and it's no longer part of the graduate admissions process. And this kind of reflects some of the rhetoric that's been used in the machine learning, like algorithmic fairness type community, and some kinds of like concepts that are being talked about, like encoding bias into machine learning systems. But there's more to this story than just the like potential for the machine learning model to encode bias. There's like somewhere along the way in the process of like choosing to build and create and release this machine learning model, something went wrong in the translation between building this model and like what the people actually want and need. So more broadly, there's an urgent need to investigate how machine learning can actually support actual education principles and goals. And that's what that's what prompted the study and what we're going to get into more today. So yeah, before getting into too much into like the results of what we're seeing, I'll talk a bit about the methods around our research study. So we talked about the grade example, but in addition to grade example, there's that grade example, there's been a lot of other places where machine learning researchers are like proposing and building models. And for this study, we compiled 20 papers from a broader survey on AI for social good, and which looked at like many domains. And we took specifically the 20 papers from education that they had, and these were published in preeminent machine learning conferences, maybe more applied machine learning conferences, such as AAAI and KDD. And we looked at these papers through the lens of interviews with 15 education researchers who were, say, like as an example, faculty in different graduate schools of education across the United States. And through talking with these interview participants, with these education researchers, we hope to gain an understanding of whether the formulation of the problems within these machine learning papers and the kinds of like metrics of success that they were using, the targets they were using to train, whether these actually aligned with the kinds of needs and goals that these education researchers saw in the education sphere. So some examples of the applications and papers, maybe similar to what we mentioned earlier, are things like predicting student dropout risk, automated essay scoring, predicting things like test question difficulty and admissions likelihood. And just to say again, like the way that we framed the interview or focused the interview was we asked, how do the paper's stated or implied goals, objectives, data, success metrics, how do these align with the actual needs and goals in education? So before diving into the findings, in order to sort of understand these findings, I'll start by precisely defining what I mean by machine learning and like the machine learning lifecycle, and provide a quick overview of the machine learning pipeline as viewed by the machine learning community. So a machine learning problem starts with a set of input data, such as previous admissions data in the grade example. And within this data, there lives a target, which is the target that the machine learning model is trying to predict. So in that grade example, this target was whether or not a given applicant was admitted in the past. And using this data, a training algorithm produces a model, and this model might have some architecture which is chosen by a practitioner or a machine learning engineer. And so this model could be like a neural network or a decision tree or logistic regression, what have you, and you decide what function you want in there. And finally, this model is evaluated on some new data to output some set of predictions so in the grade example would be a prediction for whether or not an incoming application is likely to be admitted. And a lot of work and discussion in the machine learning community has gone into addressing bias in different parts of this specific pipeline. So for example, we want to make sure the data isn't biased. So as UT Austin had recognized in their tweet, they were worried about the potential for ML to encode bias in the system. So one example here, it could be like data bias, or there's been quite a bit of work in the machine learning fairness community on like different ways to correct the kinds of different bias. So that includes like possibly enforcing constraints in the training process, such as in the admissions contest, maybe you'd want to do something like output some same number of positive admissions across different groups, or maybe you want to equalize some like true positive rates. So like given that a student will be admitted, what's the probability that the model will predict that they're going to be admitted? And maybe you want that to be similar across different like protected groups. So there's definitely like a lot to dig in there, and the machine learning community has poured quite a bit of time and attention into studying these kinds of types of measures of fairness, and where that like different unfairness can come from. But surprisingly, our interviews revealed that most of the gap, or a significant amount of the gap, between the machine learning models presented in the papers and the considerations that are required for these machine learning models to actually be useful in real settings, they actually come from outside of this box. And there's actually like an entire pipeline and life cycle outside of this box. And the full machine learning pipeline actually looks something like this, where before the problem is even created, there's a set of practitioners and researchers who need to formulate what problem they want to solve. And that includes choosing what data to use, what target to train on, and what the prediction goal even is. And these individuals, these practitioners and researchers are influenced by, or they may be influenced by all sorts of outside forces. And yeah, so that's a set of people that are there. Yeah, this happens before the problem is even like come into any kind of reality. And then once they formulated the problem, the model is trained and algorithmic bias considerations may be taken into account. And now we're in this like middle machine learning pipeline sphere or square. But then once the predictions are produced, now comes the problem of turning those predictions into interventions. So how will you actually use these predictions in policy decisions? And who will be seeing the predictions? How will the interventions resulting from the predictions actually impact education stakeholders? And of course, there's a feedback connection between the impacts on between these impacts on the education stakeholders and the practitioners and researchers formulating the problem. So they'll kind of see how their the problem they formulated maybe did in practice. And so while there's been a ton of attention from the machine learning community on this inner box, there's been way less attention paid to the rest of this pipeline, which is equally important, if not more important, to the success of student outcomes. And in the rest of this talk, we'll dive deeper into findings in these different parts of in this like broader full machine learning pipeline. And first, we'll look into important choices in the problem formulation stage that can set up a machine learning problem for success or for failure. And in part two, we'll do a deeper dive into the translation from predictions to interventions and the ways in which machine learning researchers might be able to contribute to making sure this is done more smoothly and more intentionally. So let's dive into the different choices in the problem formulation stage. This being like the first stage before the model is even like, before your machine learning model is even conceptualized. This is like a very important stage to get into. So every time a machine learning model is formulated, there's either like implicitly or explicitly some choice of some education goal. And a trend across looking at these different machine learning papers through these interviews show that there's a sort of selective interpretation of these goals. And specifically, machine learning papers tend to focus on a single quantitative metric. So an example of this is like, say, improving on-time graduation rates in the early warning system or dropout risk prediction setting. And so this kind of maybe seems practically reasonable, since in a machine learning problem, you kind of need one quantitative metric to be able to train on. And so this seems reasonable, but our interview participants identified multiple metrics that they actually care about, such as things like, oh, well, they don't limit themselves to graduation rates. They also want to look at other things like retention rates and so forth. And in addition to that, they some are also interested in like, oh, are the students graduating with satisfaction? Do they know exactly what they want to do afterwards? So that's another thing that they look at. So even like this single like quantitative metric of improving of like graduation rate or probability of graduation, that actually lives together with in like practitioners' minds with other quantitative metrics as well. But I guess here, like graduating with satisfaction is a bit harder to quantify numerically. And it's also harder to collect longer term data on what students end up doing afterwards. So like maybe 10 years or so after graduating, like it's just harder to get that longitudinal type of data. So this, so like why do ML papers focus on things like graduation rates, or what's the difference here between these is, well, generally there's a bias towards shorter term outcomes and measures that are easily quantifiable. And this bias, like, or this trend maybe makes practical sense as well. But more broadly, there's still some inherent issue and gaps that emerge around the fact that machine learning papers have to focus on just a single quantitative metric. And we've alluded a little bit to the issues around it being a single metric here, and I'm going to dive a bit more into that, and I'm going to break down actually each part of that single quantitative metric. So first, as sort of alluded to with the graduation rates, a single metric isn't really enough to capture all that's needed in the education context and capture like the full set of goals that exist. And there's actually an entire ecosystem of competing goals between stakeholders. So right now we're focusing on a single part of the single quantitative metric. So first, the student stakeholder themselves will have different axes or different sets of goals that they're going to care about. For example, they might in their classes, they might want they might want to make sure they have enough time or enough attention or enough resources. In the admissions context, a student might want some like holistic individual evaluation. They might want, and then of course the student cares about their personal learning and growth. So here, like a student stakeholder already has multiple goals, and just any like single quantitative metric isn't going to be able to capture all of these simultaneously. And some of them might maybe be in tension with each other or complement each other. And like with these, educators might mostly agree that these are important. And educators might mostly agree that there's like multiple goals that are important, but this still isn't the end of the story, and differing goals don't just stop with the student. So in fact, when it comes to those who are those at the like top part of this pipeline who are actually implementing and formulating the machine learning problems in education, these are often coming from an educational institution. And this institution has its own different sets of goals. So if the institution is, for example, like an institution might care about financial gain from high rates of student retention and graduation. And this is probably true in more in like higher education settings. And an institution might also have a goal of creating population level equity and access. So things, and especially public institutions might have some mandate to look into this. And population level is different from like individual level goals, because now you're not looking at like each individual student, you're looking at like, okay, across the board in my like student body, what is the composition? So if the institution is formulating the machine learning problem, then sometimes these institution level goals may overshadow the student goals. It's kind of like a bigger piece that's like surrounding the student goals. But we're still not, the story still doesn't end there with the institution level goals. Like even at the institution level, even above the institution level, there's policy that influences the research and development in machine learning. And there's also government level goals that influence the funding towards different research bodies and different institutions. So from the government side, funding agencies might care about, like, there's an interest in economic labor outcomes. And from the research side, there are research incentives, maybe coming from the CS side, that they want methodological novelty and improvements in prediction accuracy. So stepping back a bit, clearly like choosing a single quantitative metric is not going to appease all of these different stakeholders. And even within a given stakeholder, like it won't appease all of the different axes of goals that they have. So that's like an important thing to consider when formulating a machine learning problem. Is like, if you have to pick a single quantitative metric, like where is it fitting into this broader ecosystem? But that's still not the end of the story. And now that we've covered some of these issues with just using a single metric, I'm now going to move on to the fact that the metric has to be quantitative. So this is the second part here of like the single quantitative metric build up. So once you choose a goal, and let's say we choose like which single goal we want to like formulate our problem around, then the next question we have to ask is, to what extent a quantitative metric can even achieve one of those goals, even if we like pitch just one. So one issue that's important here is that not all goals can reduce down easily to quantifiable summaries or quantifiable measures. In particular, a qualitative individual narrative in an admission setting may be irreducible to quantitative summaries from machine learning models. So as one participant puts it, holistic admission is not about putting all these characteristics into a prediction model and then seeing what's the probability of admission. Instead, the goal is to restore the actual life experience and difficulties that the student overcame or that they overcome throughout their life experience to arrive where they are. So where do these quantitative summaries actually come into play? Well, the way this has been previously done, like with something like this, where you have a pile of applications and they pass through a machine learning model, which provides a ranking of the applications based on past admissions. And this ranking is then passed to the admissions officer, who may take into account the ranking along with the full applications themselves. And this ranking, it can be like a ranking like this can be a very coarse type of summary, and it's really like compressing down the entire application into like a single metric for ranking. And so it definitely, like, a ranking itself would not give a full picture of the actual life experience of the individuals. But I mean, maybe it's used together like with the full review of the applications, but also a ranking like this can also like bias the admissions officer quite a bit, even if they do choose to read the full applications, because they'll also have this like very coarse summary metric. So as came out of our interviews, this isn't the only way that machine learning has to be used here. And as an alternative to that very coarse quantitative summary, instead of giving an explicit ranking, the algorithmic system could give summary information to the officers that reduce the cognitive load, but aren't just like a full-on ranking. So, for example, like the alternative could look something like this, where the algorithmic system could instead produce maybe more fine-grained summary information on aspects that are more amenable to quantitative summaries. And that information could then possibly more equally interact with the rest of the application as the admissions officer like processes the full stories. So there are different ways in which we can decide which quantitative summaries to make. And as machine learning practitioners make those decisions, it is useful to keep in mind what kinds of like individual narratives are being compressed, or what things are more or less amenable to compression. So, okay, so now let's suppose that machine learning researchers have chosen some goal which is quantifiable. So having decided what to quantify, and now that we've discussed maybe some limitations around making that decision, there's still another issue on how to turn that quantitative summary into a metric with which to use to train a machine learning model, and by which to measure the success of the machine learning model. So now I'm on to the metric part of this single quantitative metric. And so here's one common example of like, what do I mean here? Like, what do I mean by a metric? Well, here's one common example of realizing a quantitative metric for training a machine learning model. So if you want to predict a student's probability of, say, passing a test, then you might need to convert some quantitative measurement that exists, such as a test score, into a binary prediction target, pass or fail, using some arbitrary threshold. So suppose we have like a bunch of test scores from students that are ranging between, say, 50 and 100, and the students are kind of distributed across this line with different test scores. And maybe there's like a few with very low scores, a few with very high scores, and then different clusters somewhere in the middle. And let's suppose that the threshold for passing a test is 70. So in the process of turning this test score into a binary pass-fail metric, there's, well, two issues that emerge here. The first is this threshold will conflate the students who are truly struggling, maybe like closer to 50, with those that are really close to the cutoff. And these are kind of two different clusters of students with different needs. So that's not maybe not going to be ideal. And another maybe pitfall here, or thing to be aware of, is that if we overvalue this line, or by creating this threshold and maybe overvaluing this specific threshold, this could lead to extra attention or extra resources going to those that are just on the boundary. So if the whole goal here is to like get students over this threshold, then maybe the like easiest way to do that, or like lowest resource needed to do that, will just be focusing on like these the students like just at that cluster, just at the boundary. But maybe those students aren't the ones that like need the resources the most. Maybe they were already like really close to passing anyway. So it's, yeah, they aren't the ones who would like benefit the most necessarily. And why pay extra attention to those versus like the ones that are just above the threshold when they're like basically very close in terms of like what their needs are, or their performance. And in addition to just like so now we've talked quite a bit about like the single quantitative metric as a target. I want to mention the choice of input as well. So by input, I mean like these are the things that are like going into the machine learning model before in order to predict some target well. And there's actually like quite a bit of discussion around the input data in the machine learning literature, so I won't spend too much time on this. But I would just add that like the bias towards easily quantifiable data or using easily quantifiable like pieces of information, this is present here in the inputs as well to the machine learning model. And in education specifically, there's an overemphasis on curricular performance that downplays maybe social and structural issues. And there's a history of theory from the social sciences that are like backing up the fact that this would be suboptimal for the machine learning model to do, to like only look at these sorts of like curricular characteristics. And this figure illustrates Bronfenbrenner's ecological systems theory, which shows that there's actually many layers of influence surrounding a child, so from like immediate schooling to family to economic situations to the structures surrounding those. So yeah, so it's important to be wary of like this easily quantifiable trap in the input space as well. And yeah, so stepping back a bit, these inputs go into formulating the machine learning problem, and these are the inputs that go into trying to do well on that like single quantitative target metric. And yeah, now that we've sort of explored both the inputs and the choice of a single quantitative metric as a target, let's shift our focus to what happens after the machine learning model is trained, or the intervention side. So often the inputs, so those inputs that we just like discussed with the maybe easily quantifiable inputs, those are chosen to maximize the accuracy of predicting that single quantitative metric as a target. And machine learning developers probably want as many relevant inputs as they can get access to, including like those in the outer circles of that Bronfenbrenner diagram. And as we discussed when predicting something like dropout risk, you probably want more than just curricular information, but also like family and financial information. And so those considerations are all going into like, oh, how do we make a model like do well at predicting this specific quantitative metric? But when it comes to actually translating these into interventions, better predictions don't always lead to better interventions. So even if we've done like the right thing or as well as we can in the like input space and in like choosing a good quantifiable target, that still might not lead to the outcomes that are desired. So more broadly, when we look at these different like papers that are published in the machine learning sphere, instead of focusing on interventions, a lot of machine learning papers talk a lot about improvements in prediction accuracy, whether it's like predicting student dropout risk or test question difficulty or likelihood of admissions. But as came out through our interviews, if computer science papers are focused on asking things like, can we predict, say, 62% accuracy instead of 61%, it's not really that helpful if nobody had anything to do that would actually like help people. Similarly, if you tell a student, or if you tell like a school that like some student has a 97% chance of dropping out based on the training data, that's a difficult thing to take in for the school, especially in public schools, where even if they hear that, it's still very difficult to find good teachers for those students, or they may not have the resources to actually intervene and act on that information. And sort of summarizing, like you don't improve things by predicting them better. So, okay, if we don't improve things by predicting them better, then like one thing one might ask is, well, what's the worst that can happen? Like we're at least predicting things better, right? Like it's, it's not like we're hurting anyone by predicting things better, right? But unfortunately, as came out through the interviews, that's still not necessarily the case. Since if papers continue to focus on just improving a specific prediction task and care isn't put into how they expect that prediction task to be translated into an intervention, then this sort of like naivety around that can still lead to harm, and harm can actually occur. And we'll call this harms of intervention unaware prediction. And an example is, so one example of this is specifically, let's look at the risk prediction setting. So in the risk prediction setting, we're like predicting the probability that a student might drop out. But showing these failure risk predictions to students can actually demotivate the students and lead to some kind of self-fulfilling prophecy. So as a student, if somebody tells you like, oh, you're not likely to graduate or you're not likely to finish a class, is that like really going to spur you to work harder, or will you kind of just be deflated? And asking that question comes from, I mean, there's like whole fields of social sciences and like behavioral research that ask those kinds of questions where, what actually motivates people. And as our interview participant says, it doesn't, if you just like show these failure risk predictions to students, maybe specifically in like a MOOC setting, where you kind of like, oh, hey, you may not finish this class, like that's not necessarily well connected to that kind of research about what motivates people. And furthermore, there's a tendency for some of these systems to stigmatize students. And this is maybe more of an issue in things like higher education or K-12. And building these kinds of risk prediction tools is quite common in machine learning papers in education and also in other fields like healthcare. So this is like a broader question here than just education. And so let's say we don't show the risk predictions to the student. So, okay, maybe showing the prediction directly to the student may not lead to like desired outcomes, but still like naive application of these predictions doesn't just affect the students, it also affects the behavior and support structure surrounding the student. So these scores will affect behavior of teachers, family, and institutions as well. So for example, with the teacher, a teacher might allocate more of their limited resources and time to other students rather than a student that a model seems to predict won't graduate. And from the school level, schools may use risk scores to filter students in ways that they think are going to work for the student. So based on like this risk prediction, they may like put students in certain classes and whatnot, or more pessimistically, they might filter students in ways that like work better for the school. So here's another like nod towards the like competing objectives and competing stakeholders in the system. Another big example is intelligent tutoring systems in addition to risk prediction. And naive use of predictive models here can also lead to worse outcomes in this like tutoring setting. So for tutoring systems, the problem here that came up in our interviews is the usage of the predictive model in ways that may overstep the limited intervention scope that would actually improve outcomes. So as our participant puts it, instead of a teaching tool, it becomes a teacher. And students might actually end up in a worse position if this sort of substitution is happening. And this is particularly like dangerous, or under-resourced schools are especially susceptible to this. And there's two reasons for that. The first being that administrators or parents might think that the teachers don't know what they're doing, or the teachers are overworked, which they are. And so way more is automated in those environments than should be. And similarly, or related to that, maybe these types of intelligent tutoring systems are used to like a high degree of success in high-performing or well-researched schools. And this success may lead to schools in struggling districts thinking it's some kind of silver bullet, but it's not used in the struggling districts in the same way, or in the under-resourced schools, because they don't have the same resources to support a like whole ecosystem or environment of like teachers and peers around these intelligent tutoring systems. Related to the intelligent tutoring system setting, there's the issue of automated grading. And with automated grading, if automated grading is deployed, then this is also susceptible to misuse and may lead to some like extreme version of teaching to the test. So this participant talks about like with a GRE, they have like an automated essay scoring tool that you can use just to study on your own. And this education expert said that like, oh, I remember learning very quickly that if I used transitional phrasing, then my score would go way up, even if the content didn't change. And like summarizing this effect, through trying to appease an automated grader, students may change aspects of their input without understanding why, except for what categorizes them as correct versus incorrect. So this is kind of a similar issue to like replacing the teacher in the intelligent tutoring system setting. And again, under-resourced schools are also more vulnerable, since with less teacher support, there's less like structure to try to tell the students, oh, this is why transitional phrases are going to work better, or like why it's maybe telling you to encouraging you towards a certain behavior. And also maybe these under-resourced schools are more heavily incentivized to do well on standardized tests for different kinds of funding incentives. So if harm can come from the naive translation from prediction models to interventions, is there a role, like where's the role for machine learning researchers in this process? It might seem like out of scope or some kind of downstream problem for of the educators, and it's like some downstream problem for them as they're creating policies and interventions. But from our interviews, there actually is opportunity for the machine learning researchers to be part of that conversation and contribute to building models that facilitate more effective interventions. So one way that came out to facilitate effective interventions is to develop machine learning models with a focus on actionability. So our participants repeatedly pointed to the value of actionable insights that can come from machine learning models. For example, as one participant puts it, we don't have to say, like, you're not going to succeed, which is what the risk prediction models are doing, like, oh, here's the probability that you will drop out. We can say instead, let's talk about what are the decisions that you need to make and what is the pathway forward that will allow you to succeed. As another example, if the machine learning model is saying like you're in the 10th percentile for something, or some like quantified metric saying, oh, you're in the 10th percentile of like the class, or like probability of doing well in the class. That sounds really different from a more actionable insight, such as, oh, we're worried because you've been absent a lot. There's like a specific behavior that that might be correlated with your probability of doing well. And why do I say actionability versus interpretability here? Well, in the machine learning community, the term interpretability has been used quite a bit to mean a number of different things. And one common usage, which has showed up in many papers in our study, is in terms of like feature importance rating. So here's an example of like a feature importance plot, which shows the relative weight that a model places on each given feature, or each given input that goes into the model. And while this feature importance was popular, it's not actually what's necessarily useful to education practitioners. And as this participant puts it, what is most interesting to them is not like, I wonder if the demographic factors matter more than the behavioral factors in this model. To them, it's more about what can we actually do to help kids get off a trajectory that they're on if they're not on a good trajectory. And maybe the kinds of tools that are used to answer this like actionability question aren't quite the same as these like feature importance type tools, and maybe tools that are more like causal based. And in addition to actionability, there's also the question of who is taking action. And that's where the second part of designing more intervention aware predictions comes in, which is designing for dedicated human operators. And there's in the education pipeline, there's like tons of very dedicated human operators, like teachers and advisors that spend all their time just trying to like make sure students do well. And with tutoring tools, for example, instead of having those replace these like very important teachers, or teachers that are like very present and aware, they can, maybe these tutoring tools can actually improve student outcomes if they're used as part of a balanced breakfast alongside peers and teachers and textbooks. And ITS here is an acronym for Intelligent Tutoring System. And this is, in the words of our interview participant, first, like a student might look online or ask a friend, and if that doesn't help, then you ask another friend, and if that doesn't help, then you go to the teacher. And so that way the teacher is sort of able to distribute themselves a little bit more evenly. So here, like if the intelligent tutoring system is part of this balanced breakfast and part of this broader ecosystem of tools, then it can actually help to distribute the load from the teacher and allow the teacher to like be able to pay more attention in the areas that count. And in addition to teachers, there's also advisors, and advisors are like a very central component to things like higher education, and also in K-12. And these advisors can come in and help students out when things like automated chatbots or like search engines and things like that run into a problem where effective usage of these automated chatbots like requires the student knowing what to query. But students don't know what they don't know. So where a student can get held up is not knowing what question that they need to ask. So in an example interaction between an advisor and a student, where the machine learning model might or the computational like automated chatbot or something, where this machine learning model might like interact with the advisor or tell the advisor is, hey, like that student's not going to be a nurse. like, sorry, like, good luck. Or if, I mean, even worse, if it like just told the student directly that, like, that might not actually be very helpful. But let's say that like, oh, this information, this like risk prediction that comes from this machine learning model in the framework that we discussed is, let's say this risk prediction just goes to the advisor, and the advisor sees, okay, that student's maybe not likely to be a nurse, but the advisor has like other information about the student from conversations with the student. So the advisor might be able to say, okay, maybe a nurse path isn't going to work out. There's also respiratory therapy, nutrition, bioinformatics, and these all these check 3 boxes that like this that they've discussed with a student, like helping people, working in healthcare, and getting a job. So the advisor takes that information from the model and processes it into something that like they might be able to use as like actionable recommendations for the student. And the student, upon hearing that, might be like, oh, that sounds great. I had no idea what an occupational therapist even was. So the student like doesn't know what they don't know. They don't know what they could have even asked to like maybe a chatbot system, and they wouldn't have known how to process like just the like, you're not going to pass your like nursing course. So in this like loop with like this dedicated human advisor, you actually can achieve the or get around some of the limitations with like these automated chatbots themselves. So stepping out back a bit, like what's the path forward for researchers in general? We've talked about the problem formulation stage, we've talked about the intervention stage, and like kind of gone through this whole like full pipeline. And as mentioned before, most of the previous attention within the machine learning community has been focused in this narrow view of the machine learning pipeline, where you just, and even like more narrowly on specifically data. But as we've seen, this is just an inner piece of a bigger full pipeline, and many pieces that lead to positive and negative outcomes for students like come from this bigger full pipeline. So this full pipeline includes the decisions that practitioners and researchers make when deciding on the problem formulation, including that single quantitative metric that they have to use as a target, as well as like a decision on the inputs. And there's also this piece on the translation from the machine learning predictions to the actual interventions. So in education and beyond, there's significant room for machine learning researchers and socio-technical researchers to contribute to both of these areas, both the problem formulation and the translation from predictions to interventions. And while we've used education as a case study today, while many of the insights from education, or actually many of these insights from education may also extend beyond to other domains as well. And some of these effects have already been studied in other settings, but there's still a lot of the focus like falls within that inner machine learning like box pipeline. So there's a lot more work to be done here, and a lot of opportunity for interdisciplinary work, both in and some other like settings include healthcare and the criminal justice and legal system, the social sector and environmental protection, and beyond. So as this like interdisciplinary work continues, I look forward to continuing this conversation with all of you from all different disciplines and backgrounds. So yes, thank you. And if you have any other questions, feel free to send me an email, and I'd also like to recognize my co-authors, Lydia, Talani, and Radiat. Thank you.
Great, thank you so much, Serena. That's really interesting, and there's a lot there to unpack. I think we should let you field people's questions if you want to do that. We have a relatively small group, so it should be possible to sort of be informal about that. So why don't I just turn the floor over, and folks can raise their hands or unmute or otherwise get Serena's attention.
Yes, I have. But I'm sorry, I don't know how to pronounce your.
Thank you. Hi, Serena, and thank you very much for the insightful talk. I really like your analysis of the boundaries at which we recognize the limitations of the systems we are building. And I am a computer scientist, so I understand, when student is ready to graduate, student publish the paper, and the paper is not necessarily considering the aspects of the usability and the fairness of its use that you're analyzing. But let me, I'm not sure I agree necessarily with the path forward that you are proposing for the following reason. Let's assume that we're not talking about machine learning, we're talking about building bridges. And the people who design bridges and eventually build bridges start with civil engineers, and they design it, they decide on which side of the river they're going to put the foot of the bridge, and so on and so forth. They have certain specifications, which are technical specifications. What civil engineers are not concerned about is whose land is going to be used for the access to the bridge. Is the use of that land for the access road going to be disenfranchising certain populations? So who is taking care about these things outside of the technical realm? Well, there are regulations, and there are societal organizations and governmental organizations that are taking care of the access roads and the access to bridges and functionality of the bridges, connection to the highway network, right? So my point is, should we really expect from machine learning researchers being civil engineers, that's the metaphor I'm making, to be socio-ethical researchers and to understand all these aspects that they're just not familiar with, or at least not experts in, right? Mm-hmm. Or we are the country that doesn't regulate privacy. We are the country that doesn't regulate pretty much anything that has to do with IT or information technology or internet. I think there is a gap between your path forward and the way how that can be realized, and that's the role of the government and the role of legislature.
I think that's I think that's an excellent point. So thank you so much for bringing that up, because this is a really that's a really good point, and a really important question that we've also been thinking about quite a bit. And the analogy to a bridge building. So I guess continuing with your analogy in the civil engineering setting, I think one difference between that setting and what we're currently doing with machine learning is that, well, in that civil engineering setting, if you're just building a bridge, it's quite clear where the lines are, as far as okay, as a civil engineer, you can say, oh, I know the physics of how this bridge is going to work. You can, and of course, that kind of development. I'm not saying that that's not important. I mean, as a computer scientist by discipline myself, I also work a lot on those kinds of development of algorithms. But I think one difference is when machine learning, the ways in which it's currently applied is, I think, a bit less mature than maybe the civil engineering area, where they're there's kind of a clear-cut line on where whose job is what. Oh, I want to build a highway that's going to be structurally sound or something, or a bridge that will work well. And then who decides where it's placed? Well, that's a pretty clear line of okay, this is somebody else, what someone else is doing. But in this sort of less mature, with machine learning, I think it's still there's still questions around what are the roles and where can computer scientists contribute, and what are the most important problems to consider when building this bridge. So I think in the bridge building example, there's probably a time when the civil engineers had to decide, oh, what are the important parts, aspects of this bridge building that we need to focus on, things they probably had to decide at some point, oh, should we try to build the longest bridge ever? Should we try to make sure that it won't collapse? Should it be really tall? What do people need? So they're deciding what ways in which what things to focus on and what problems to attack is that might have come from outer conversations with the government, where they're oh, you need to make sure your bridge doesn't collapse. I think we're still kind of in that phase with machine learning, where there's still questions of, well, where should we be putting the focus? Should we be trying to predict the most accurate things ever? Let's go all in on full accuracy on risk prediction, or maybe instead, oh, what's the analogy to something that's structurally sound here? So I think that's more the conversation we're trying to foster is there's what's happening currently inside of this like machine learning square is very like, maybe there's been like a lot of effort in like very specific directions from the machine learning community and like trends. But I think we're, as a field, like where our role is not quite like as clearly defined yet. So that would be my like, my counterpoint there. But as you say, I think that's a really like good question. And like, what is the role of like, what is the right place for like machine learning researchers here to interface with like the government, and what is the role of policy in shaping these conversations? And I think it's so fluid right now that like I don't think we can quite say that the lines are clearly drawn.
Thank you.
Yeah, but thank you for that great question.
So maybe I'll ask a question as well, or Gordon, go ahead. You raise your hand.
No, I'm moderating. You should go first.
All right. So to a little bit of Boyan's point, but the regulatory environment. So how much should this be regulated and how much should it not? A lot of this is in one industry, finance is starting to be regulated. I wouldn't say they're perfect yet, and we still have all the old examples of redlining and that. But the regulatory environment around model risk management from the Federal Reserve is really outlining how to do this and how to start to look at bias and information in all of the models within finance. Is that the right path that we should be expanding beyond, or are there other ways to do this interaction between the researchers and understanding as the models are being built what potential biases and getting the right stakeholders at the right points in the process to be able to do this?
Yeah, that's a really good question. So you say like there's regulation coming from like
Federal Reserve.
Federal Reserve. Okay, and that's specifically around like
it's around how to manage models and when and how, and they're starting, and it's probably only the last 2 years they started talking about bias, but the banks are being audited for their bias and for bias within their models and the interventions. And so that process has started. It's been long in the making since the financial crisis of 08, 09. But the Federal Reserve and the Office of the Comptroller of the Currency are the ones that are kind of forcing this on the banks, but it doesn't seem to be known very much elsewhere.
Yeah, that's an interesting question because, and I think I'm probably not familiar enough with that setting to be able to say exactly like what the right role would be, but I mean, it sounds like if I'm hearing what you're saying correctly, that like there is thought into like what bias looks like in that setting, or like how you, and that seems to kind of be a tackle of like this inner like blue box of like.
So it's when the models predict, so they build all the models and the predictions, but before they can deploy it, you have to validate it. And one of the validation checks is basically bias and inappropriate implications of the modeling as they put it into production. So it's an attempt, right? We as social researchers talk a lot about, hey, this model is bad, that model is bad, right? We're implementing bias, but for the people that are actually trying to put this into production and utilize this in the systems, they're trying to make it work as best they can. So they have a process by which they're checking. And that's where I like to poke, is what's the right process, where you should bring in the right stakeholders. Yes, you're going to have your computer scientists, but you have a team around them that are checking and doing things. So
yeah, I think that's a really excellent question. So what I would add there is that in the auditing process, or in that like checking process, like my understanding of how a lot of things are currently done in my experience in industry as well, is that like you kind of have, yeah, like maybe there's like some metric that you want to like run your model through, or you can like quantify some like measurement of bias. But I think what like the way that would relate to this talk is that like the choice of that measurement is really is important. And like what does that actually, how does that measurement of bias actually like correlate with real outcomes, or like what are you trying to like do using that metric? And if it's just one metric, well, are there like multiple metrics that we should?
There's never just one metric when in the finance industry, but yes, I see your point.
Yeah, so I think that's in that like decision around that metric, like that's maybe where other stakeholders will be brought in. And then I think from the CS side, I guess to sorry, is it Boyan? Is that how you pronounce it? Okay, thank you. Yeah, maybe from the CS side, like there's questions of like, well, what if is that metric like going to be optimizable? Is it something that like is reasonable to like to use as something with which to measure the performance of your machine learning system? So there's like, maybe what I'm saying is there's room for like an interdisciplinary conversation there. Oh yeah, Gordon, I think you had your.
Yeah, thanks. So I had a thought and then a question. The thought is just that, I mean, education is so heavily regulated in a lot of ways, and there's a real pressure to have metrics and things you can like rank schools and do all of that. So I wonder if education is a particularly good area to look at these topics in, because there is a fairly high regulatory pressure to come up with quantifiable metrics, which then looks, to be very attractive to use machine learning, even when maybe you shouldn't be doing that, right? So I think education, I mean, it's not as regulated as finance, but there's an awful lot of pressure to have, metrics that you can put up on dashboards and, this is a B school, that's a C school or whatever. The question is, and I'm asking this, I know more about the criminal justice system work on this, and there's some literature that talks about what happens when people interact with the outcomes of machine learning systems. So I'm thinking about, so like it wasn't a machine learning system, but Kentucky implemented a sort of mandatory risk score bail assessment data point the judges were then using in pretrial risk assessment. And when they looked at what happened when judges started using it, was really strange. Like it did reduce the amount of pretrial detention. That was the goal, but it did it in racially disparate ways. And it depended upon the exact demographics of the county where the judge was, the extent to which white people were benefited more by the system than Black people. So I wonder if is there work of that sort in education about the interaction between the, whatever metric you pick, and then how it changes how people interpret. Yeah, in other words, along the model of the risk scores in jails.
Yeah, that's a good question. Wait, may I ask, like, what do you mean by like the? I guess could you go a little bit more into what you mean by the way that the metric was interpreted?
Yeah, so you sort of have this goal of reducing the number of people who are incarcerated pre-trial. And so prior to the sort of debacle over the Compass system, there was this rule in Kentucky that judges had to at least look at a risk prediction score. Mm-hmm. And I remember the paper about this, the judges weren't using the risk prediction score in the way that anybody expected them to. And so there were various racial biases that creeped in, but it wasn't even predictable what a judge would do. You had to look at not just the judge, but the county they served in, the demographic breakdown of that county, the kinds of people that they saw before them. And so one of the sort of pressure points here at the intervention level is just that it's very hard to know what people are going to do with the outcome of the ML, right?
Yeah.
They have this, even if you have a perfect metric, right? Even if we assume that the risk score prediction is totally accurate, you still don't know what the practitioners are going to do with it when they have it. So I'm just wondering if there's work along those lines in education.
Yeah, you mean like work along, like how do we determine what the practitioner is going to do, or like recommendations for what the practitioner will do with it? Or?
Yeah, and so the system says recommend that you get. It doesn't just give information. It doesn't say 80% likely to drop out. It says recommend that you email this person every day to prod them to keep coming to class or something, right? Do we know what teachers or educators or other people involved would actually do with that kind of advice?
This is a really good question. I think, yes, that's a really good question, because it kind of goes like a couple, like maybe a step ahead of like what our paper is even doing, where it's like, okay, now let's look at like, or maybe, I mean, it's similar to some of the conversations that we've had. I think my short answer is like, I think there's not like that much like work that's been done. I think there's still like a lot of opportunity for more work to be done there, as far as like how are people actually going to use some of these recommendations or models. And okay, so maybe like, okay, one step above, like just here, let's give like a risk prediction is, okay, let's give some actionable recommendations to the stakeholders. And then one like step, I think another like avenue of exploration beyond that is like, well, how do these like stakeholders actually interact with that kind of recommendation? And I mean, I guess, yeah, like those are like along the lines of like questions that we're trying to ask here. Yeah, I think if your question is like whether there's been a lot of work there, I think the answer is not much, or as far as I understand, like I don't know of a whole lot. And yeah, I think that is an important like area to look at and one that we're trying to look at.
Yeah, thanks. I was actually motivated by what do we know about how teachers assign grades, or how when teachers, what's the decision-making process that teachers use? Because we need to know that to know how it's going to interact with machine learning. So that's actually where I was going with that. There's sort of like there's a whole area of like really weird psychology and sociology to try to understand.
I think that's a super really great point. And that I think similar conversations like that came up in our exploration of like, well, what's the intervention that actually is useful to the teachers in these different settings? So like in the advising setting, it was like, yeah, what does like a useful, what kinds of like targets are useful for machine learning models to try to predict or insights that they want to create in these settings. So like with the advising setting, it was things like, oh, if you can like, maybe instead of just saying, here's a student's risk of dropping out, like it's maybe more helpful for the model to provide things like, oh, here, like the student like not doing well in this class is like correlated with their like, was correlated with other students not finishing this like major, or the student has like, maybe like attendance is like one issue that seems to be coming up for the student, and that might start other conversations with the advisor about like maybe reasons why attendance might be an issue, and like maybe broader conversations about like financial aid and whatnot as well. So yeah, I think that kind of conversation did come up in like maybe like slightly different settings, and in the grading setting too, there's that like, yeah, I think I agree that like, or similarly to what you're saying, like it's useful to understand like what the actual process is that's even being used by these like human operators, like the teacher who's doing the grading or like the advisor who's doing the advising, before you can to like help us best decide what choices to make when developing a machine learning model to like actually help in these settings.
You guys have managed to time this exactly to 1:15, about which I am very impressed. So if there are no further questions, let's join me in thanking Serena for the talk. All right, yeah, the thanks are coming up in the chat. All right, well, in that case, I would like to encourage everyone to come hear about a totally different topic in the African research paper on the 28th, and then to join us for the next one of these with Alex Hanna. Thanks, everybody.
Thank you.